Hi, I'm Alan, and today I'll be talking about an optimal trade-off between entanglement and copy complexity for quantum state tomography. This is joint work with Sitan Chen and Jerry Lee. So let me begin with the basic setup. So quantum state tomography is probably the most basic quantum learning task. So there is some unknown quantum state rho, which is a d by d PSD matrix with trace 1. And we're given some copies of rho and we can make some quantum measurements on them. And at the end of the day, our goal is to learn a description of a quantum state rho hat that is close to rho. Now, there are a few fundamental resources in quantum state tomography, and the most obvious one is copies of rho. So we'll think of only having a limited number of copies, say n copies of rho that we're allowed to measure. However, copies of rho are not the only resource. And another important resource consideration is quantum entanglement. And so since quantum entanglement is expensive and difficult to maintain in practice, we'll think of only being able to make entangled measurements over a limited number of copies, say t copies of rho simultaneously. And so, as mentioned, these are both practically motivated considerations because obtaining fresh copies and making highly entangled measurements are both difficult and expensive. So the main question we'll seek to address in this talk is, can we trade off between entanglement and fresh copies? Or in other words, can we save copies by using more entanglement in our measurements or vice versa? So what is the relationship between these two basic resources in quantum state tomography? Okay, so now let me discuss the formal measurement and learning model. So we'll think of the learner as being able to make measurements over t entangled copies of rho simultaneously. So it can make measurements of the state rho tensor to the t, which is a d to the t by d to the t dimensional quantum state. And so the learner makes measurements of the state via the standard formalism of POVM. So a POVM is, so the learner chooses a collection of PSD matrices, say M sub C, that sum to identity. And then when they measure the state, they observe an outcome Z corresponding to an element of their POVM with probability equal to trace of rho tensor to the t times M sub C. And so now, note that this is a valid probability distribution because the matrices sum to identity. So these probabilities sum to 1, and they're all non-negative because the matrices are PSD. And so now the full learning process is as follows. So the learner first chooses their first POVM M sub 1, then they measure one like t copy batch, so rho tensor to the t, and they obtain some outcome Z1. And then now sequentially, now they can design a second POVM M sub 2, possibly adaptively, measure a second t copy batch rho tensor to the t, and then so on, for up to n over t total iterations. So the learner uses a total of up to n copies of rho in batches of size t. Now, the main question we'll seek to address in this talk is for a given t, we want to learn an unknown quantum state rho to epsilon accuracy and trace distance. So how many copies n do we need? And I think this is a nice question because we have a very limited understanding of sort of the relationship between the two basic resources of fresh copies and quantum entanglement. And I think this is an important consideration as we gradually scale up our quantum devices. So first, let me say a few words about prior work. So basically, prior work addresses the extremes of t is equal to 1 and t is equal to n. So in the extreme of t is equal to n, this corresponds to making fully entangled measurements. And so for this case, there were these works by Ha, Haro, Ji, Wu, and Yu, and also O'Donnell and Wright in 2016, where they show that the optimal sample complexity in this case is n is d squared over epsilon squared. On the other hand, the extreme of t equals 1 corresponds to single copy or unentangled measurements. And so here there was an upper bound of d cubed over epsilon squared shown by Kuhn, Rahut, and Terstege in 2017. And then in 2023, the same authors, along with a few others, we showed a matching lower bound. However, even though we understand the extremes of t is equal to 1 and t is equal to n, it seems that nothing was known in between these two extremes, even for t is equal to 2. So there's literally nothing known in this intermediate regime. Now, while t equals 2 might seem silly, there are actually many natural quantum learning tests, such as estimating Pauli observables, where t is equal to 2 actually is significantly stronger or like significantly more efficient than t is equal to 1. So there's perhaps some natural reasons why so little is known in this intermediate regime between the two extremes of t is equal to 1 and t is equal to n. And so this is because the approaches for these two extremes are fundamentally incompatible. What I mean by this is, so the approaches using entangled measurements are based on one-shot algorithms that actually construct a bias estimator for the state rho, but they show that the bias is small as the number of copies is sufficiently large. On the other hand, the approach is based on unentangled measurements. So these algorithms average many copies of a highly noisy but unbiased estimator. And so these approaches are like kind of incompatible. And so if we want to succeed in some intermediate regime, then we want to be able to aggregate our information over n over t batches of size t. But it is not clear how to do so without first designing an unbiased estimator for these like t entangled batches. And so this leaves the natural question. So can we really hope for a smooth trade-off between these two extremes? Or does the incompatibility between the two approaches mean that there is really some hard phase transition where entanglement only helps above a certain point? So our main result is that there is actually a smooth and optimal trade-off for many regimes of t, d, and epsilon. And to our knowledge, this is actually the first smooth trade-off between entanglement and copies for any natural quantum learning task. And so, okay, specifically, so we say a state tomography algorithm is successful if it learns to trace distance epsilon with high probability. And so for our upper bound, we show that, so for some regime of t, at most this like d over epsilon to some positive constant c. And so in this regime, n is equal to d cubed over root t epsilon squared total copies suffice for quantum state for learning to trace distance epsilon. And we also show a matching lower bound. So again, d cubed over root t epsilon squared copies are actually necessary for some regime of t here. So let me say a few words and give some interpretation of our results. So our upper and lower bounds are listed here. So they're both d cubed over root t epsilon squared with some restrictions on the regime of t under which they hold. So the first thing is that when epsilon is small, we fully characterize the trade-off. So when epsilon is sufficiently small, our upper and lower bounds are tight for all possible, for like the full regime of all possible values of t. So we recover the existing rates when t is equal to 1 and when t is equal to d squared. And so an interesting consequence of our results is actually that you never need more than t is equal to d squared entanglement, even when epsilon is like very, very small. So you actually have like d squared over epsilon squared copies. So this actually gives a small qualitative improvement over previous algorithms, which required like sort of d squared over epsilon squared entangled copies to get the optimal sample complexity. But we show that actually you only ever need to entangle d squared copies at once. And furthermore, even when epsilon is not small, so even in the constant epsilon regime, we give a non-trivial improvement in the upper bound. So we give a polynomial improvement in the upper bound, even when epsilon is constant. And so, okay, we believe that this d cubed over root t epsilon squared should be optimal. However, there are some technical difficulties. So we have these like additional like technical restrictions on the regimes of t under which our trade-off holds. Okay, so now let me say a bit about the technical part of our algorithm. So first, our algorithm consists of two steps at a high level. So the first step is what we call the balance case. So in the balance case, so what we mean by this is when rho is somewhat close to maximally mixed, we'll give an algorithm for estimating rho. And the reason why this case is nice is that sort of when rho is somewhat close to maximally mixed, we can actually control the bias of a natural t entangled estimator and then sort of average our estimator over a bunch of batches. So next, when rho is not necessarily close to maximally mixed, we'll design a splitting procedure to reduce to the balance case. All right, so let me first discuss the balance case first. And yeah, so in the balance case, so our framework, our basic framework will be as follows. So we'll design an estimator with small bias from measuring rho tensor to the t, and then we'll average this estimator over all our batches. And so, okay, so we measure some POVM rho tensor to the t. So we'll log our POVM is rank 1. So its elements are of the form some weight omega z times zz transpose where z is some vector in this d to the t dimensional space. And so anyway, so we measure this POVM, and then we have this estimator f, which maps the output of our POVM to some matrix, some d by d matrix that is supposed to be an estimator for rho. And so we can easily compute the mean of our estimator. So the mean of our estimator is simply the sort of integral or sum over the POVM, weighted by the probability of seeing a given outcome z, which is given by this inner product in the red. And so now, okay, so the first thing is, okay, so when rho is somewhat close to maximally mixed, so we write rho as identity over d plus some error e. So the key idea is first, when e is small, we can actually approximate this like t entangled copies of rho, this rho tensor to the t, with its first order truncation. So we can instead write rho sub t to be the d to the t by d to the t matrix that is given by sort of the linear approximation to rho tensor to the t. So we just keep identity over d tensor to the t plus this linear approximation to this tensor product. So this symmetric sum is over sort of all possible ways to tensor together one copy of e and t minus one copies of identity over t. Now, so the main takeaway from this is that when e is small, we can actually replace rho tensor to the t with rho sub t while incurring only some small approximation error when e is small. And so then we can, so incurring this small error, we can then pretend that we are actually measuring rho sub t instead of rho tensor to the t. And so now this linear approximation is significantly easier to analyze. And so in fact, if we were working with this linear approximation instead of the true state, then we could actually get an unbiased estimator for e from measuring sort of this linear approximation rho sub t. And so sort of the entire bias in our estimator just comes from sort of the error in this first order truncation. And that once we make this truncation, we can now get an unbiased estimator for rho. Okay, so now let's discuss how we can design the estimator. So recall, okay, so what do we do? So we have the mean of the estimator, and then we replace this t entangled copies of rho with the linear approximation. And then then we can write the mean of our estimator as the following expression, where basically all we did is we used the fact that rho sub t is a linear function of e. And so therefore we can sort of rewrite this inner product as the inner product between e and some like explicit linear function of the entries of ZZ transpose that I will not specify for now. But M of Z is like some linear function of the entries of ZZ transpose. And so now we want the estimator to estimate rho, which is the same as estimating E. So it turns out the optimal choice is just f of z is equal to m of, so actually f of z is equal to this function m of z listed here. And sort of maybe some intuition for why this is natural and optimal is that sort of the signal is kind of the correlation between f and m. And we're kind of subject to a variance constraint because the variance kind of scales with f squared. So the natural and optimal choice actually turns out to just that be to set f of z equal to this expression m of z. And now the signal to noise ratio of our estimator, so we can do some computations and show that basically it is controlled by sort of this average value of Frobenius norm of m of z squared. And so we will show that we can actually achieve a signal to noise ratio of t to the 1.5 and that this is optimal. So we can show that after some computation that the sample complexity should be d cubed t over epsilon squared q, where q, so then substituting in q is t to the 1.5 will give you like the d cubed root t epsilon squared sample complexity claimed at the beginning. Okay, so next, so now we have reduced the problem to bounding a quantity that governs the signal to noise ratio of our estimator. So the remaining question is, so we have this like POVM specified by like omega z z transpose that is, so recall it's a POVM, so this sort of the z's have to be isotropic or like they average to identity. And now the question is, how can we maximize the signal to noise ratio quantity q specified as follows under the constraint that the z's form a POVM. So in other words, for a collection of isotropic z's, how large can the typical value of the Frobenius norm of m of z squared be? So to understand this, we'll need to understand this matricization M of Z a little bit more. So we'll start by getting a bit of a more explicit handle on this matrix M of Z. And so recall the definition. And now it will be instructive. So I won't like give an explicit formula, but you can write that down. Instead, it will be instructive to consider the following example. So consider when Z is actually a tensor product of t d-dimensional vectors. We have some orthonormal bases v1 through vd, and Z is a tensor product of, say, k1 copies of v1, k2 copies of v2, and so on. So in this case, we can evaluate that actually what we want M of Z to be is actually we want it to just be k1 v1 v1 transpose plus dot 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 plus kd vd vd transpose. And then the squared Frobenius norm of M of Z is just k1 squared plus dot 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 plus kd squared. And so roughly this gives us the following important intuition, which is that we can relate the Frobenius norm of M of Z squared to some notion of partitions of T into at most D parts, and we can sort of make this relationship via some representation theory. So we define a partition of T into at most D parts. So we just have a list of D non-negative integers that are sorted, non-negative, and sum to T. And so this is our partition. And then we can write the L2 of the partition lambda to be just the sum of the squares of the elements of the partition. So for example, here we have a partition of 8 into 3 parts given by 4, 3, and 1. Now, the key lemma will allow us to relate this Frobenius norm of M of Z squared to the projection of Z onto various subspaces that are indexed by partitions of T. So specifically, this theorem Schur-Weil duality from representation theory says that there is a canonical decomposition of this D to the T dimensional space as a direct sum of subspaces that are indexed by partitions of T. So indexed by partitions lambda of T into at most D parts. So these subspaces are indexed by partitions of T into at most D parts. And now our key lemma is as follows. So our key lemma is that for a vector Z in this D to the T dimensional space, then the Frobenius norm of M of Z squared is at most this quantity on the right, which is just the average L2 norm of the partitions of the spaces that corresponding to the subspaces that Z lives in. So we have basically this average over so we have this like average over the L2 norm of lambda that's kind of weighted by the projection of Z onto these different subspaces, so pi sub lambda. So this inequality seems to go the wrong way because, again, we want to maximize M sub Z. However, the key is that the equality cases in this lemma will guide our solution to the optimization problem. So there is a sufficiently rich family of Z achieving equality in this sort of inequality above, and this family of Z achieving approximate equality will be, so understanding this family will be crucial for the design of our POVM. So, okay, so recall the question we want to understand is we want to maximize the signal to noise ratio quantity. And we have this key lemma that sort of upper bounds this Frobenius norm of M of Z squared as a function of the projection of Z onto the various Schur subspaces corresponding to these partitions. And so we know that approximate equality holds for a sufficiently rich family of Z. So we'll design a POVM where equality holds for actually all of the elements Z in our POVM. And so via some representation theory, we'll show that, okay, we can actually construct such a POVM. And so if we were able to construct such a POVM, so achieving approximate equality in this key lemma, then we would have that sort of the signal to noise ratio quantity Q is approximately just 1 over D to the T times, so if we just like plug expression 1 into, so if we plug the key lemma into the expression of the signal to noise ratio and we integrate over all Z, so using the fact that the Z's are isotropic, we know that the total weight on any subspace pi sub lambda must be actually just equal to its dimension, again, because the Z's are isotropic. So then the signal ratio to quantity Q will just be this average over these partitions lambda of the dimension of lambda times the L2 norm of the partition lambda. So again, once we construct a POVM achieving approximate equality in the key lemma, then we have the following expression for the signal to noise ratio. And now the key is that the right-hand side is actually just a statistic about random partitions of T drawn from some distribution called the Schur-Weil distribution. And so this quantity on the right-hand side, we actually is just a combinatorial expression that is well understood. And so actually the value of the right-hand side is actually just T to the 1.5. This is like a well understood quantity. And roughly this is, the intuition for this is just that a typical partition roughly has root T parts of size root T. And so this will give you the L2 norm of T to the 1.5. And so putting everything together, this gives us the desired bound on the signal to noise ratio. Okay, so finally, so recall there are two parts to our algorithm. So the previous part, we've addressed the sort of optimal estimator and the balance case. And finally, we need to discuss sort of a splitting reduction, where how we reduce from general states rho to the balance case. And so, okay, the splitting procedure will work as follows. So we just want to transform a state rho into a new state we call split of rho, such that split of rho is close to balance, and we can simulate measurement access to copies of this like split state given copies of rho. And then we'll run our learning algorithm on this split state and argue that it gives a good estimate, that somehow we can like back out a good estimate of rho from our estimate of the split state. And so very roughly how our splitting algorithm works is, okay, so we obtain a estimate rho hat for rho, then we diagonalize it. And then finally, so working in the basis in which rho is diagonal, so here working in the U basis, then we'll basically split each row and column of I into a number of different rows and columns. So if the eigenvalue is alpha I, then we'll split this row and column into d times alpha I different rows and columns. So basically for each large eigenvalue, we'll just like split it up into a bunch of smaller eigenvalues spread over multiple rows and columns. We can show that, okay, this blows up the total dimensionality by at most constant factor, but this splits up the large eigenvalues of rho so that we end up with something that is close to balance. And yeah, okay, so that's the reduction. Okay, so now to briefly summarize, so we give a smooth and optimal trade-off between entanglement and copy complexity for quantum state tomography and many regimes. This is the first smooth trade-off known for any natural quantum learning task. And so the technical tools are, so first we use this linear approximation to get an estimator with small bias when rho is kind of balanced, so kind of close to maximally mixed. However, even with the linearization, we still need some representation theory and sort of understanding these distributions over partitions drawn from the Schur-Weil distribution to bound the signal to noise ratio of our estimator. And finally, for general states rho, we give a splitting algorithm to reduce to the balance case. So this is the sort of putting everything together. And so I'll conclude my talk there. Thank you.